In this video, we are going to learn about informed search. Before we begin to learn about informed search, we need to know first what we have learned so far. So previously, we have learned about uninformed or blind search, in which most of the algorithm in this blind search they are very inefficient because all the possible alternatives are being explored. So it will take a longer time for the system to come out with the appropriate results that we expect to have. Therefore, we can add some domain knowledge to improve this search process. Hence, informed search is a search algorithm or search process with the domain knowledge added onto the process. In some reference, informed search also known as heuristic search, in which domain-specific information are added into the search algorithm in order to select the best path along which to continue the search process. In the heuristic or informed search, all the nodes that is most likely to the nearest to a goal state will be explored. How can we create an informed search algorithm? Before we begin, we must define a heuristic function or the so-called HN here that will estimate the goodness of a node n. Specifically, let's say that this heuristic n function, it will estimate the cost or the distance of the minimal cost path from n to a goal state. Again, remember that the heuristic function itself is only an estimation. It's not the exact value. It's only an estimate that will likely lead the computer to the expected result. So this domain knowledge itself are based on the domain-specific information, based on the problem and all the limitation that is given. That is computable. Remember here, this is the very important characteristic. It must be computable from the current state description of how close we are to a goal if we take that move. Okay, let's see what are the methods that can be used to provide this kind of a specific domain knowledge to improve our search algorithm. Hill climbing and greedy search or best first search algorithm. This is what we are going to learn in this week. And then there's also branch and bound algorithm, or people also refer to the uniform cost search. We will learn about this in the later weeks. And then A-star search algorithm. This is also we will later in the later week. Okay, first let's see how hill climbing works, or what is the so-called hill climbing search algorithm. In the hill climbing search algorithm, it works as follows. If there exists a successor, the so-called node S, for the current state n, such that looks one step ahead in order to determine if any successor that node n has is better than the current state. If there is, then we will move to the best successor. One important characteristic in this hill climbing search is that it does not allow backtracking or jumping to an alternative path, because in hill climbing, the algorithm itself does not remember where it has been. Okay, let's see on the examples of this hill climbing search algorithm. Okay, let's see how to solve these 8 puzzles in the hill climbing. So first of all, before we begin the search, then we must define, right, what is the heuristic function that we are going to use. In this case, the heuristic function that we are going to use is the number of tiles that is out of place. In this case, the smaller the value of Hn, the smaller the value of tiles that is out of place, then it means we are closer to our goal. Okay, let's see. Given the start state looks as follows. Then let's see what will be our goal state. The goal state will be as follows, in which the blank tile must be in the middle. So let's compute what is the value for our heuristic. it will be the number of tiles that is out of place. Let's count how many tiles that is out of place from between the current state, this one, which is the start state right now, compare it with our goal state. Okay, we have this one, number 2, 8, 1, and 6. So we got 4 tiles that is out of place. In this case, what we can do is that we can move these blank tiles. So when we move these blank tiles, what kind of move that we can make? We can move to the left, we can move it up, or we can move it to the right. Then we know if we move to the left, then there will be 5 tiles that are out of place. If we move the blank tiles from our start state to up, then we'll have 3 tiles that are out of place. If we move it to the right, we have 5 tiles that are out of place. In this case, we will choose the smaller value of hn, right? The smaller value of our heuristic function, then it will lead us closer to our goal. So in this case, we will choose move up. So this is our current state right now. So from here, we know that how many tiles that is out of place? That are out of place? 2, 1, and 8. So we have 3 tiles. So in this case, we generate what are the next move. So these blank tiles, it can move to the left, it can move up, and then it can also move to the right. How about move down? Well, basically this informed search also follow the same basic algorithm as the one that we use in the uninformed search, which is the forbidden move that will create a loop solution will not be selected. So obviously we cannot move down because we just move these blank tiles up. Right, so if we move right, so again we will still get the same edge, right? The same heuristic that does not change, the same tree. If we move up, again we still also have the same heuristic that does not change. If we move right, we have a bigger heuristic. Since we have 2 smaller heuristic that we can choose, either move left or move up, we can choose anyone, right? Okay, so for example, in these examples, let's say if we pick move up, if the algorithm choose move up, again we will compute for the next generations how many move and how many the value of each heuristic that for each move before it can determine the next move. From here, it can either move left or move right. If this blank tile choose to move right, then we'll get 4 heuristic value. But if it choose to move left, then we will get only 2. Again, choose the smaller value of heuristic. This one should be chosen, and then we'll get this state. Next, again, we will generate the next possible solution. These blank tiles can only have one move at this moment, which is move down, right? Moving down, it can only move down. It cannot move to the right. In this case, since we only left with one option, then this will be our default next successor. Move down, this one. And from here, we know that this blank tile, it can either move down or move right. If it moves down, the heuristic value is 2, but if it moves right, the heuristic will become 0. Choose the smaller value of hn. So in this case, we choose this one, just move right. In that case, we will get our goal state. Let's see another example of hill climbing algorithm. So imagine that we have the following tree in which the start here with the value of 25. If the heuristic value, if the heuristic function that we determine here, there can be 2 possible heuristics that we can use. The first one will be the number of nodes that's being traversed, and the second heuristic will be the shortest distance. So if we want to search the solutions for this tree using the heuristic of the number of nodes traversed, given that our goal state is edge, the node edge here, then what we must see, it will be the number right beside the node name. Let's say here start, the heuristic value that we will use is 25. If node A, the heuristic value is 16, node C, 10, node T 13, node P 19, node P again 18, node P again 11, node G 29, node J 30, node I 0. So if the number of nodes, if our heuristic is the number of nodes traversed, and then our goal state is node H this one, in this case our solution would be from the start here we see the value 25. We generate there are two successors of start, either node A or node B. We see node A here has a value of 16, meanwhile node B is 19. So obviously we will choose node A. Again, from here we still have not reached node H because our goal set is not H. So in this case, we will compare it again. Our algorithm will compare again. What are the child nodes of node A? It's either node C or node T. Again, we will see node C has a heuristic value 10, node T has a heuristic value 13. So we will obviously choose node C. Again, coming back again, node C, it has two child nodes, node G and node H. Node G is 29, node H is 18. And coincidentally, node H is our goal state. So in this case, we will choose node H. So our solution will be from the start here, we go to A, to C, and then we get to H. Okay, let's see another example. What if we change our heuristic function to some other value? Let's say here, the heuristic function that we will use in the second case will be the shortest distance. And the goal state, let's say, is node K. Then the value for this heuristic that we will need to look will be the differences between the two nodes. The value above the line. From start to A, there's 28 distance. From start to B, there is 10. A to C is 15. A to D is 8. D to B is 7. And another B to B also 11. Let's see here. From the start, okay, it has two child, either to A or to B. Because the value of heuristic in B here, the distance is smaller than the value from start to A. So node B will be our selected successor. Again, node B here, it has two child, B and P, B left and B right. Alright, let me put it, this is B1 and this is B2. Okay, let's see on the heuristic, the shortest distance. B to B1 is 7, B to B2 is 11. So the next successor will be B1. Again, from B1 here, it has two child nodes, K and L. From P1 to K is 16, from P1 to L is 29. And since K is also our goal set, so this K with the heuristic 16 will be chosen for the next successor. Remember here, given the problem, it's possible that for a problem to have two heuristic functions, and these two heuristic functions may lead to different goal state, may lead to a different solution. See you again on the next video.